Bernoulli's equation describes the relationship between pressure, velocity, and elevation of a flowing fluid. We will be demonstrating 3 experiments that show the application of Bernoulli's equation and principle. The Bernoulli's equation was first published by the Swiss physicist Daniel Bernoulli in 1738. We can think of Bernoulli's equation as a conservation of energy. It says that along a streamline, the sum of the pressure, kinetic energy, and gravitational energy remains constant. This conservation of energy gives rise to Bernoulli's principle that states that an increase in velocity must be accompanied by a decrease in pressure. To explain Bernoulli's principle, we will take 2 points in a pipe as shown in the picture. As the 2 points are on the same height, the gravitational energy will remain constant. Looking at the continuity equation, density remains the same. Thus, the equation can be rearranged to this. Since A2 is smaller than A1, V2 will be larger than V1. Going back to Bernoulli's equation, as the total energy remains constant, the increase in velocity will cause a decrease in pressure. Therefore, high velocity equals low pressure and low velocity equals high pressure. Now on to the experiments.
When the hairdryer is switched on, the stream of air above the paper has a higher velocity. This causes the pressure of the region above the paper to be low. This situation can be explained by Bernoulli's principle, which states that an increase in the speed of a fluid would result in a decrease in pressure due to the principle of conservation of energy. The pressure below the paper is atmospheric pressure, which is higher than the air pressure above the paper. The higher atmospheric pressure generates a lift which can overcome the weight of the paper and push the paper upwards.
The ball is suspended in a high-velocity stream from the hairdryer, which by Bernoulli's principle is generally a low-pressure zone. Outside that stream is the atmosphere, with a much higher atmospheric pressure and a much lower surrounding air velocity. As a result, the higher atmospheric pressure prevents the lower pressure from pushing the ball out of the airstream. The overarching concept for this phenomenon is Bernoulli's principle, but can be further discerned by another concept known as the Coanda effect. At given instances, the spherical bluff body of the ping pong ball deflects the stream of air from the hairdryer. The air streams past the stationary air particles surrounding the ball with high velocity. Due to viscosity, the deflected airflow pulls the stationary air particles along with it, creating the low pressure regions which will pull the moving airflow back towards the ball. This tendency for moving air or fluids to stay attached to a curved, convex surface in a low pressure region is called the Coanda effect, which keeps the ball from leaving the low pressure zone. Earlier concepts pertain more towards the lateral displacement of the ball. For vertical displacement, the ball would only remain floating if the velocity of the air approximately equates the drag force acting on the ball to its weight minus buoyancy force to achieve force balance.
In this experiment, the ball is attracted to the stream of water. As the stream of water has a higher velocity as compared to the air, the pressure of the stream of water will be lower than the air in the atmosphere. This is supported by Bernoulli's principle, which states that the higher the velocity of a fluid, the lower the pressure. Due to the higher pressure of the air in the atmosphere, the ping pong ball is constantly pushed back into the water by the air in the atmosphere, even though the gravity tries to pull the ball downward and out of the water.
This experiment is also a demonstration of the Coanda effect. As mentioned earlier, the Coanda effect is a tendency of a fluid with higher velocity to stay attached to a convex surface. Since the stream of water, fluid with higher velocity than atmospheric air, is constantly attached to the ping pong ball, a convex surface, this experiment is also a demonstration of the Coanda effect. That's it from us. Thank you.